So Recons is sort of what I set up back in the 90s. And it's interesting to hear someone say graduating in 1986. That seems like a long time ago now. But it's been an interesting journey since, and a lot of it's been through the solar neighborhood. So I set up Recons a long time ago, and we have some sort of fundamental questions that we're after here. And that's, the little ones, like what is the universe made out of? Where are the planets that we might find? And ultimately, where is the life perhaps on those planets? And of course, my career has spanned all of these, and it was sort of fun to work with Carl Sagan and Jill Tarter and think about life in the universe pretty much for a career. And as I would tell anybody, if you can find your favorite hobby and then get someone to pay you to do it, you've done pretty well. That's the way to go. So tonight, we're going to start with a little bit of perspective, right? This is a mock-up of our galaxy. You guys know it's called the Milky Way. From the the chatter I heard from the business meeting, I can tell that you folks actually know some things, so I can probably not have to back off too much when I describe some of the things that we're going to touch on tonight. There will be graphs, there will be plots, so we can interpret those together, but I think you guys can handle most of it. If not, just jump in and stop me. So here is the Milky Way. It's not a real picture, of course, because we haven't sent any probes up above the disk of the Milky Way galaxy to take this picture. But I will put something in the middle there that's 30 kiloparsecs across, and there's a little black dot in the middle there. That is the supermassive black hole that everybody thinks controls the whole galaxy, but of course it really doesn't. It might have a few million times the mass of the sun, but that is nothing compared to the roughly 100 billion to a trillion masses that we have in the Milky Way itself. So things are swirling around, but it's more around the mass that's sort of towards the center. And tonight, we're going to talk about a little piece of the solar neighborhood out here that's only about 100 parsecs across. And so that little yellow dot there on the right sort of marks where we are, roughly 2/3 or a half of the way out from the center of the galaxy to the edge. But the edge of the galaxy is very hard to define. And in fact, I'm teaching a graduate course in galactic structure right now and poking at the students all the time, trying to say, where is the edge of the Milky Way? And we're talking about Cepheid variables and RLI stars and gas and dust and distributions of things in the galaxy, trying to see the edge. So we don't really know exactly where the edge is, but we're roughly halfway out. And we're going to center that on the sun, of course, because we can be a little Ptolemean here and think that we're at the center of the universe, even though we're really Copernicans and we know we're not. So first things first, I wasn't sure what this crowd was going to be like, so I had to at least throw in the parallax slide or two. So you take a baby astronomer and you say to that astronomer, you want to measure the distance to that star, because defining the solar neighborhood or a nearby star means you have to know the distance. And we use something called parallax for that. I'm assuming everyone in the room knows what a parallax is, but for a quick review, you take the two telescopes in your head. Those are, in fact, pictures of my retinae, because my partner is an optometrist and I have access to cool machines that can do this kind of stuff. So those are my two telescopes in my head. And of course, I can measure a parallax to the star with my eyes if that star is close enough. But of course, we learned over hundreds, if not a few thousand years, that measuring the distance to a star is actually tough because the angular shift is very, very small, especially from your eyes. That's not nearly enough to do it. So what do we do instead? We sit on this little marble called the Earth, and we go around the star called the Sun, and we look at a star that's relatively nearby and measure its position relative to stars that are further away. We call those background stars or reference stars. And then we wait 6 months and we do it again. And we look for another position of that star relative to the background stars. And then we measure the angle in between, which is actually the trigonometric parallax, right? That's how we measure these kinds of things. And in fact, now that I know this crowd is fairly erudite, I can tell you that's really twice the trigonometric parallax, because the baseline we use to measure trigonometric parallax is 1 astronomical unit, not 2, which is the full extent of the Earth's orbit, plus or minus a little bit that you can take care of with the math. So that's how we do a parallax. But I do want to do the exercise, and I now can see the room. So I want everybody to hold that thumb up in front of your face and hold it out at arm's length. Close one eye against that scale. Maybe use the top scale, because centimeters are real units, not those silly inches on the bottom. And close one eye and measure where the position of your thumb is, and then close the other eye and measure the position of the thumb, and you should see it move. If it doesn't move, you need to see your friendly neighborhood optometrist because you need to get that checked out. So that's basically what we're doing, except we're using the Earth's orbit instead of each of our eyes to measure the distances to the stars and getting those angles called the trigonometric parallax. So I was asked before we started, do I have a favorite star? I will say this is a top few. This one would go on the podium at the Olympics of one of my favorite three stars called GJ 1061. The GJ stands for Gliese and Yarais, the great gods of nearby star work for about 50 years, spanning all the way to the 1990s. And GJ 1061 became a focus of our efforts because it looked like from spectroscopic and photometric evidence that it was about the same color and the same spectral type as Proxima Centauri. And we all know, I hope, that Proxima Centauri is the nearest star to the sun. And so we got very interested in this star. We compared it to some other stars that people also thought were very nearby. It turns out the other three were giants that were just mimicking a dwarf kind of star, but this one turned out to be a dwarf. And in fact, we found that this was the 20th nearest star. And it amazed me back in the early 90s that we didn't know this. And so this is sort of where the whole RECONS concept came out of. And it made enough waves in the press before there was much internet that a little telescope called Sky and Telescope picked up the story, and it was all about the 20th nearest star and our discovery of it. And I don't know if you can see my cursor. Can you see it? Yeah. So this up here is the same issue of Sky and Telescope where they talked about life on Mars as discovered by the rock. The little tiny fossil-like evidence, supposedly, of a little critter inside fossilized in a Martian rock. Well, it turned out one of these two results was more believable, and Sky and Telescope made the right call as to which one to put on the center of the magazine cover, because that one turned out not to be true. That was not evidence of life on Mars at all. So the obvious question came to me, are there any more of these very nearby stars that people have not discovered? And that comes back to this graph that we made back in the day. And along the bottom here is the parallax, where the left-hand side are the closer stars and the further stars are on the right-hand side. And this goes out to 0.1 arc seconds, which means 10 parsecs. And that's sort of the core sample we're going to talk about today. So each dot represented a stellar system within 10 parsecs of the sun. And we just kept incrementing by one every time we got to the next star system. And you can see there's sort of this nice curve in the black dots. But if you assume that you know all the stars within 5 parsecs, then the number of dots should follow the red curve. And we should have a lot more systems, over 300 of them, within 10 parsecs compared to what we knew back in 1997. So the difference between that red line and the black dots indicates we are missing nearby stars, a lot of them. And so that's why RECONS was created, to discover and characterize all these stars and their companions, including substellar objects and planets in the solar neighborhood. We're basically trying to build a 3D map around the sun so that we know when the Starship Enterprise takes off where it's actually going to go, or maybe where at least the next probes will go if we go to interstellar space. Now, a little primer sort of on objects. I think most of the folks actually know these things here, but we have stars up here like the sun. We have smaller stars. Then we have things called brown dwarfs that are substellar objects. Then we have planets, and we now know that we can have Jupiters that are gas giants. We can have terrestrial planets like the Earth. We can have ice giants in between like Neptune and Uranus. And now we've got some other funky kinds of worlds going on other stars, at least we think from the data we have, like super Earths and sub-Neptunes are two more categories that people talk about. And you folks probably know this. Again, I wasn't sure of the crowd, but that's a G star and that's an M star. How many people in the room? Raise your hands if you know all your spectral types. That's what I thought. Okay. Well, the G star is what the sun is. We have the larger stars that are the F dwarfs, the A dwarfs, and then we have the two big ones. Those are the O and B stars, right? These are all dwarf stars. We're not talking about giants or supergiants. And these are all large compared to the sun. Now, the O and the B stars are very rare. That's going to come into play in a minute. But of course, we have the other two categories of main sequence stars that most people talk about. And those are the K dwarfs that we study a lot in Team Recons, and the M dwarfs, which are also called red dwarfs. Yeah, I will interchangeably say M dwarfs and red dwarfs. If I say one, I mean both. They're all sort of the same thing. They are the smallest of all the stars and the ones we're going to spend most of our time talking about today because it turns out they run the universe. So let's look at what's in 10 parsecs. The O and the B stars go away. There's nothing there. We just have these 5 types left, but I'm not going to give you the punchline yet because I'm going to let you join the research endeavor with me and go through about 10 or 20 years of trying to discover what the solar neighborhood's actually made out of. So in order to get this moment of illumination from a rainbow from New Zealand in a picture I took, it takes help, right? I'm not ridiculous. I'm not going to try to do all this myself. These are sort of the Fab Five first graduate students in the Recons group. When I got to Atlanta, you can see they have PhDs spreading over about a decade. And these are the 5 folks who did all the really core work to pull all of this to fruition and actually get us some population statistics of what makes up the universe. What we did in the meantime to do this is we took over some telescopes. Now, how many of you folks in the room actually have your own telescopes? Okay, so you know what it's like to have your own telescope. I chose to try to swipe one from a place called Cerro Tololo that you've probably heard of in the Chilean Andes, in the foothills of the Chilean Andes at 7,000 feet. And there is a picture of the summit. There are about another 20 telescopes that are down off the summit now in what we call the mushroom field, which are almost all robots. And in fact, the 2 on the left are either closed or robots, and the 3 on the right are the ones that are still working. And we made a consortium called the Small and Moderate Aperture Research Telescope System. I cannot claim credit for that acronym of SMARTS, but I do love it. These are the SMARTS telescope. And those of us who use them are sometimes called the Smarties because we were smart enough to get a hold of these. So in 1999, I started a 3-year project on this little 0.9 meter telescope, and it turns out we're still going. So you never know. You got to be careful what you start because it may turn out to be so good that you just can't stop. And that's what's happened there. A few years ago, well, actually 9 years ago now, I took over this other telescope as well. So now we have 2 telescopes on the mountain that we're running all the time. And in fact, as soon as I leave you tonight, I will be checking in with Madison LeBlanc on that 0.9 meter telescope and Tim Johns on the 1.5 meter telescope because they are there observing right now. They've been observing, I think this is night 10 of 14. And so I will check in with them and see how things are going at those telescopes. We still have people at those telescopes because humans are still useful, it turns out, to be at telescopes because you can make changes on the fly faster than you can probably train a robot to do it right. And you have more processing ability in your head to realize which particular science project can be performed the best in the conditions in the sky as they're changing, whether or not clouds come in and the seeing changes. So I think all of you will probably agree with the following statement. The reason we took on the 1.5 meter was I learned there's only one thing better in the world than having your own telescope, and that's having 2. And sometimes we actually use these together and look at the same star at the same time. The larger telescope does spectroscopy, the smaller telescope does imaging and photometry, so we can get simultaneous data in multiple ways. We do go to Chile, as I mentioned, to use these telescopes. We are never really alone. This particular video was taken during the COVID pandemic, just when we were getting folks back on the mountain. And of course, that room is completely sanitized and you have no problems inside the room, but you might have a roommate if you open the door just the right way. We do have tarantulas there. We do have scorpions there. This is a high, dry desert, and those are the kind of animals that you can have as friends on the mountain all the time. So the 0.9 meter is where we've done most of our work over the longest period of time. We are now in year 27 on this telescope. I call this the best telescope in the world. That's what it looks like from the outside. This is what it looks like from the inside, and it truly is the best telescope in the world. How do I get away with saying that and knowing it's legitimate? Well, We have now had over 2,000 nights on this telescope, and not a single one of those 2,000 nights was lost because of the telescope. We might have lost it because of weather, of course. Maybe the dome didn't work. Maybe the camera didn't work. Maybe the computers didn't work. But the telescope itself has never been responsible for losing a night. So I do think it is the best telescope in the world. And if any of you actually want to go to Chile sometime and maybe get a tour, I can probably arrange that. So it is a beautiful site. It's not like New Jersey. I heard you talking a little bit about filters and images that were taken. I got to say, some of those images were pretty nice. I don't know how many of them were taken in New Jersey. As I mentioned to some of you before, I'm from Pennsylvania, so I understand the skies there. If you get a clear night, you run outside and do the best you can with it because they tend to be rare. But in Chile, they're not rare at all. 200 to 250 nights a year will be totally clear. And then the other ones, you might have to battle some clouds once in a while or the occasional snowstorm. But that is a picture of the 0.9 meter with the center of the galaxy in the background. That is a real picture taken by my friend Travis Rector, who's an astrophotographer. It's a pretty nice place to be if you want to do astrophotography. So, how do you find new nearby stars? You team up with somebody, right? The world is actually small. It's not a very big planet we live on. And I teamed up with a guy I didn't know very well, but I'd met him at a conference or two. And Nigel Hambley over at the University of Edinburgh and I decided to work together on something called the Supercosmos RECON Survey. And so if you ever see in the literature something, a star that has the initials SCR, that stands for Supercosmos Recons, you know what Recons is. It's just a group of us doing science. Supercosmos was a big machine the size of multiple desks that was scanning glass plates and getting data off of those plates that have been taken over 50 years. And there's a map there on the bottom of the galaxy, well, actually the entire sky, with the galaxy plane along the horizontal axis, and each one of those dots is a source in supercosmos. And we've all heard about big data, which was a term that sort of got started being used in 2010-ish. We were using a data source with almost 2 billion dots in it back in the early 2000s. So I didn't even know I was doing big data before big data became a term. It's kind of fun to be on the cutting edge when you haven't even defined what it is you're doing. So we used big data. We looked at all these dots. We got a bunch of numbers out that talked about things like proper motion, which probably most of you know. This is an series of images taken at the 0.9 meter telescope over 10 years. That is Proxima Centauri sliding along the sky in front of those background stars because, of course, Proxima Centauri is near to us, the sun is moving, Proxima is moving, and the relative motion is projected onto the background stars as a vector. And so Proxima's proper motion is large because it's so close to us. If it were 10 times further away, it would only be 1/10 as fast. So we can use proper motion numbers in both directions, right ascension and declination, and we can pick out the stars we think are probably nearby. And that's exactly what Nigel and I did with a bunch of students. And what I didn't know was going to happen was that when we started observing at this 0.9 meter telescope, again for 3 years, I thought we'd find a handful, maybe, of nearby stars. What I didn't realize is that we would literally be buried in discoveries. It turned out it was happy hunting grounds in the southern hemisphere because most of the historical parallax work was done in the north, where most people live and where most telescopes were and the facilities were used for that. There was very little done in the south, and so it was very easy for us to make a new discovery. And we got literally inundated with all the kinds of discoveries that we could make, which made students and their advisor very happy over many years. So what did it actually look like as we did this? Well, I don't know if any of you in the room are familiar with what's called the Yale Parallax Catalog, but this was the ground truth back in the day in 1995. And there were about 191 systems known within 10 parsecs of the sun back in 1995 that were in that catalog. It was put together by a guy named Bill Van Altena, who is a legend in astrometry and parallax work. And he was the one who pulled it all together from all the observatories from all over the world. So that's what we had a starting point in 95. Then the Hipparcos space mission came along and added a dozen or so new nearby systems, but Hipparcos didn't go very faint. So it couldn't see red dwarfs very well. And that's where we discovered that GJ 1061 star that I mentioned before in 1997. That's sort of where RECON's really launched. Another sort of 50 years went by, and nobody really found much of anything. We were churning away collecting data because we started at the telescope in 1999. And then every time you see a little red number there, we published a paper that added new star systems to the 10 parsec sample. We had a big paper in 2006. Then we had a little trickle of people. Most of those increases there are actually brown dwarf discoveries within 10 parsecs, not stars. This particular plot includes those as well. Anytime, again, you see a red number, we publish something, and then we sort of wrapped it up in 2018 and published another 14. And if you add all those numbers up, you get a little over 40. It turns out some of them were right sort of at 9.9 parsecs, and better measurements moved them to 10.1, so they don't officially fall in the sample anymore. But in the end, we found 40 different systems that were nearby stars, one of which turned out to be a brown dwarf. So we have 39 new star systems within 10 parsecs of the sun. Now, for you folks, I'm sure you're asking one big question. Did it make a difference? It made a huge difference, right? 66% increase in the number of star systems known within 10 parsecs, I think is a pretty good show. It wasn't just us in this case. Again, this includes the brown dwarfs, which we weren't focused on, but it's a large increase in the population. So imagine that you're living in New Jersey and you have 190 people in your neighborhood, and all of a sudden you now have over 300 people in your neighborhood. That's going to be a big change. And that's what the solar neighborhood now looks like. But you're probably also asking, what about Gaia? How many people in the room know what I'm talking about when I say Gaia? I'm talking about a spaceship. Yeah. Okay, so Gaia is a European mission that was launched in 2015 and surveyed the sky. And it also collected nearly 2 billion data points. But in this case, all those data points, instead of just proper motions and colors like supercosmos, all of those data points come with parallaxes. Now, not all those are useful because a lot of them are very small, close to zero. And so that's not going to give you much. But they did scan the entire sky. And you can probably guess it's going to find all kinds of new things near the sun. But it turns out, folks, we did a really good job. Gaia discovered exactly one new star within 10 parsecs, and our little team found 40 new systems. So I would say we kind of beat Gaia to the punch on this one in a big way. Now, they certainly found more things beyond 10 parsecs. We were focused on anything within 25. They discovered thousands within 25 parsecs. We discovered about 300 or 400 within 25 parsecs. So, but for 10 parsecs, we pretty much swept the board. And Wei-Chun Zhao and I, you'll see his picture coming up in a little bit. He was the first graduate student in the RECONS group. You saw him actually earlier. He and I wrote a reviews article last year or 2 years ago now, and it gives you the final answer, folks. This is it. This is the number of different kinds of stars there are within 10 parsecs of the sun. This does not include the brown dwarfs. That's a separate discussion we can have. But these are the numbers. And what you should notice right away is that the big numbers are down here in the K dwarfs and the M dwarfs. Again, the M dwarfs are the red dwarfs, and the K dwarfs are just their bigger cousins. And the K dwarfs are actually very close in size and mass and temperature to our sun, a G dwarf. So the Ks are a lot like the Gs, but they're a little bit smaller. They last a lot longer. They burn a little cooler on their surface temperatures. And so they're actually really good places to live. And that's going to be important a little bit later in the talk. So remember this graph? We had the stars moving. We had the 5 categories. I left you with question marks. And now you know the answer. Instead of question marks, we have these numbers. 75% of all the stars in the solar neighborhood, and presumably the galaxy, and likely the universe, are these little M red dwarfs. That's a huge number. And if you ignore those little red stars, then you're missing most of the game out there. But if you're clever and astute, you probably just added up those numbers and said, but wait, that's not 100%. Can anybody in the room there tell me what's missing? Or online? I'll give you some hints. They're small, they're and they used to be bigger stars. Yeah, these are the white dwarfs. So about 6% of the southern neighborhood is made up of dead stars, right? These were AF and G stars that have already puffed off their outer layers and gone through the planetary nebula stage. And now you see the core that's left over and they cool over time. But they're very faint and very small, maybe only the size of the Earth, as opposed to the smallest M dwarf, which is about the size of Jupiter. So these are very, very tiny little hot embers left over from the cores of those stars. And that is the 100%. And that is the mock-up slide that I started this whole talk with. And this is now become sort of one of our logos for recons. You can actually see there's one A star, two Fs, 5Gs, 11Ks, 75 Ms, and six little white dwarfs hidden in there. We actually have these stickers that if I were physically there, I'd be handing out to you. And it's sort of an eye test to see who can find the white dwarfs nestled in there among the other stars. But the point of this little schematic here is that it's sort of a powerful marble diagram of what the universe is made out of. There are some O and B stars, but they're so rare, they really don't matter that much. This is really what you need to pay attention to. And so in recons, we have focused on the 86% of stars that dominate the universe. So what I want to do now is pose some science questions. I'm always poking at the students saying, okay, folks, you want to do some sort of study? What's your science question? What are you trying to answer? When it comes to 86% of the stars in the universe, we want to know how old they are. We want to know whether or not they're active. We want to know if they have companions beside them, what the orbits of those companions look like, and are there any planets going around them? But of course, if you're savvy, you looked at all five of those and you know where I'm headed with this. There's one big question left. Where is it a good place to live? It's got to be the right age. It probably shouldn't be too active. It's probably not in a multiple system, but if it is, the orbits have to be big or very small, and the planet either has to go around one of the stars with a distant stellar companion or around both stars where the two stars are close and the planet is outside that. And all of these factors come into play as to whether or not even planets can be created and whether or not they're going to be any place good to live. So, how are we going to do this? We're going to put together a team K and a team M for the two different kinds of stars. And Wei Chun and I, again, he graduated in 2004, but he's decided to hang around because all the job offers he got weren't as good as doing the research we're doing in the Recons group. And he's really enjoyed it there, I think, most of the time. And Team K, this was sort of the four folks who are still working on the K dwarfs. This was a new effort for us, and this sort of all came together when we took over that telescope. And now Team M has expanded to six people who are still actively working on the M dwarfs. All of them are PhD students in the group now, or they've already graduated. Jen Winters, in fact, is actually a professor up in Massachusetts. Elliot Vrymoot is now a pseudo professor also in Massachusetts. Hadari is a professor here in Atlanta. And the other folks are postdocs or graduate students currently. And so we're pushing on the K dwarfs and the M dwarfs. But the first thing you have to do is collect them. We've been doing that for the M dwarfs for a long time, but now we're going to go further afield because we want to get great statistics on larger samples than only a few hundred stars. We want to get into the thousands. So this was our pandemic puppy Miles, who's actually just to my left, lying down now, twice the size. And Miles was saying, I want to collect all the K dwarfs and all the M dwarfs I possibly can. How are you going to do this? And we really launched this effort during the pandemic. We decided we'd go out to 50 parsecs for K dwarfs because Gaia will get us a complete sample. And we'd go out to 25 parsecs for M dwarfs because Gaia can help us get there. Can't get them all, but it can get most of them. And you can see the numbers there, over 4,000 K dwarfs and over 3,000 M dwarfs. These are the kind of meaty samples you have to work with, but they're not so large that you can't treat them as friends. You get to know them well enough, at least if your brain still works and can catalog this kind of stuff. We do have spreadsheets, we do have databases, we do have all those things, but we also know a lot about individual objects. And so the question is, can you check and vet them carefully enough? Not vet as in going to see the vet, although Miles is okay with the vet, but we do check and vet every single one of these so we understand what's going on in the systems. So Miles keeps looking at us going, well, okay, that's great, but what's the point? Why are you actually going to do this? Reason number one, we all know this. you want to know who your neighbors are, right? Because if you really know your neighbors, then you understand what's going on in your neighborhood. We also want to know what to observe, right? We are providing the world with the very best observing lists to do all kinds of surveys, whether they're for planets or other astrophysical kinds of things like multiplicity, activity, all those kinds of things. We have the world's best samples of both the K and the M dwarfs. And finally, the statistical basis is what RECONS is all about. How often do these stars have planets? Why don't they have them if they don't have planets? Some people say that every star has a planet on average. That may or may not be true. And in fact, I'm almost sure it's not true. Only if you add up, that some stars have 5 or 10 planets going around them, will you average out to one? But there's a lot of astrophysics and understanding buried in the numbers in these large samples, and you only know statistically what they are if you study them very carefully. So let's do a quick tour of M dwarfs and some of the science we're trying to do. First, we're going to do rotation. Why would you care about the rotation of an M dwarf star? It turns out that most stars are like all of us. As we get older, we slow down. I'm sure some of you in the audience know that uh, because we've all been through it, right? Things rotate quickly when they're born, they move fast, as they spin, and then over time, magnetic braking, which is the magnetic fields locking into materials of its disk or winds of material leaving the stars, actually slows them down over time. So you can get an age estimate of a star if you know the spin rate, which is the rotation. Do stars have spot cycles like the sun? We know the sun goes up and down every 11 years because it's got a solar cycle. Do other stars have that? The only way you can figure that out is if you have a lot of data over a lot of time. And there aren't a lot of groups in the world that can focus on things for long periods of time. And then what are the orbital architectures? So if I have a star going on another star, what do those orbits look like? Is it different if it's a brown dwarf? Is it different again if it's a planet? Only if you can map all these things out will you ever know how did you form a binary star system? How did you form a planetary system? Do they form in similar ways or are they different? So these are the kinds of science questions we're asking. You may have your own. So let's start with the rotation. You might have heard of another spaceship out there called TESS. This is the one that's up there trying to find the transiting Earth-like solar system objects. This is the Transit Exoplanet Sky Survey, I think is what TESS actually stands for. I've forgotten. I just said TESS for so many years now. And this thing has 4 telescopes you can see there pointed, and it rotates around the sky and sits on a certain field and then shifts after about 27 days and moves to another field. And it keeps doing this, looking for transits of planets passing in front of the stars. You can do a lot of astrophysics with this as well. This is what's called a light curve from the TESS spacecraft. Along the horizontal axis there, you see days. So you can see that this goes from 2695 to 2715. That's 20 days. And there's this oscillating period here. That is a star spot or a collection of star spots on one side of this little M dwarf star spinning around as it rotates, and it comes in and out of view, and it changes the brightness of the star. This delta magnitude over here is in millimegs. So that 10 means it's 0.1% of, 1%. That's a 1% change in the flux coming from the star. And if you try to match up all this and phase it up, you will find out that this star is spinning every 21 hours. And so it's just a very easy measurement for TESS to make. However, TESS can't do them all. TESS is looking at a big piece of sky at once, and so it gets into crowded fields and it cannot measure the individual dots. You have to go to a little telescope like the one we have down in Chile at the 0.9 meter, and you can do follow-up and disentangle confused sources and see objects like this. This is a particularly fun one to do because I looked at it in one night, and it only took me 2.5 hours to get the whole rotation period. Again, this star has spots on it. You can see that the flexure in that light curve is a factor of 5 larger than the one on the left. So this one is changing by 5% in its light. So this was a very easy measurement for us to make at that little telescope. We can also do the cycles work. And I mentioned you can only do this if you have a long data set. So This is what it looks like for the sun. You can see here 1980 on the left, 2000 on the right. That's 20 years. The sun has a spot cycle where actually it's bright, then faint, then bright, then faint every 11 years. In fact, the sun is brighter when it has more spots because the faculae around the spots are the dark regions that are cooler, the faculae are hotter and brighter on the edge. It makes the sun actually a little bit brighter. And you can see it's going up and down over time. But the question is, do other stars actually do this? Especially the M dwarfs. Nobody's really done this before for M dwarfs. We know that other solar type stars show this, but we've been looking at some of these stars for over 20 years now at this little telescope, and we've now seen exactly the same kind of thing on these little small red stars. Each one of those points is an image taken on a night. We typically take 5 per night. That's why you see the little clusters of 5. And you can see the overall pattern looks very much like the sun there. This one, however, has a period of 16 years just for one cycle, whereas the sun has 11. We have one here that's almost 20 years long. And I'm happy to say, as I just mentioned, Madison's down there right now, and she's making more measurements. So we're continuing to follow about 450 stars to see if they have cycles, see if they have companions pulling on them, and doing other science as well, getting the rotation periods when we need them. But I kind of faked you out a little bit here because these graphs look the same. It's a bit of a ruse. So we now know that star spot cycles exist on other stars, but the scale was a cheat. This scale up here on the top is actually inflated compared to the one below. That's the plot on the same scale. So the sun is bouncing up and down by only 0.2%. I think most people in the crowd know the sun is not causing climate change. It just doesn't change by enough. Instead, we have these little red dwarfs that are changing by 5% on the left and 8% on the right. So these are much more radical changes by factors of 25 to 40 compared to that of the sun. So now imagine you're sitting on a planet having whatever sort of drink you like, and you're looking up at your star and wondering what it's going to be like a few years later because it's going to drop by 8% in brightness. So your days are going to change your weather is going to change based on what your star is doing instead of on what the weather on your planet is doing, probably by more than the weather on the planet in some cases. Proxima Centauri, by the way, is the most variable of all the red dwarfs we're looking at. It varies by almost 10%. However, it's not in a nice cyclical way. It's got some random things going on that we need a lot more data to try to tease out. Maybe it's a 100-year period with other weird oscillations that are smaller. Okay, then we can also look for companions. This is a mock-up of a star in the middle with something smaller going around it. It could be a smaller star, it could be a brown dwarf, it could be a planet. Generally, if it's another star, we can use special techniques to actually see that star. But if you can't see the star, what we do is we just see the wobble of the primary in the center. And we break that into the two directions in the sky, right ascension, declination, and we can map that out over time. So some cases we see both stars. In those cases, we can go to a telescope like this one, which is the SOAR telescope, also in Chile. It's on the next mountain over from the one where I operate my two telescopes. We've used this one quite a bit. And here you can measure orbits of stars. And you can notice up here on the right, this was a very easy observation to make over less than 1 year. It only took about 8 months for one companion star to go around the primary star. Sometimes you have to go longer. These are a few points over here on the right that we measured at the SOAR telescope, but there was some data from other sources. You can put those data together, and that's just barely enough. You can make a fair guess that the period of this orbit is about 30 years. These are cases in which we can see both stars. We can actually map that going around. There are cases at the 0.9 meter telescope, and we go to SOAR, and we can't see the companion. Instead, what we see is this. This is that perturbation in the right ascension declination on the top, and the right ascension on the top and the declination on the bottom, broken into the two axes and watching the wobble of that star in the middle going back and forth. Now, the funny thing about this is if you look at the scale on the bottom, that's the year in which the data were taken. So we started back in 1999. We started this one just after the millennium. And something very important happened right there, just after the millennium. Madison LeBlanc, who's at that telescope right now, was born. So we have now been looking at some of these stars for longer than the graduate students have been alive. And that is Madison at the telescope holding up what we call a finder chart to be able to find the star so that she can point the telescope at it and get the next set of data. So we now have data streams that are longer than the lifetimes of some of the students working on them, which is actually pretty cool. And there's really nowhere else in the world that has this kind of data set. And we can do science that other people can't do. We get the orbital periods from a few months up to 30 years because we have such a long data set at this telescope. And this is a curious result that Ellie Vreimuth came up with for his thesis work. He's got about 200 orbits plotted on here. Now, on the y-axis, we've got the eccentricity, so that's the shape of the orbit. And on the horizontal axis, we have the orbital period. That could be same on major axis, same idea. So this is basically the size and the shapes of the orbits of the companions going around these little red dwarfs. And you'll notice something a little weird. There's a box here with almost nobody home. Some of these are a little bit rare cases that we'd have to look at more carefully, but there are very few dots there. What this means, circular orbits along the bottom, here at zero eccentricity, there are effectively, once you hit 10 years, none of the orbits are circles anymore. And that says a lot about how these formed. These did not form in a disk that had dissipating forces that would make you sort of get herded into a circular orbit. Instead, these are probably primordial evidence of how the two stars coalesced near each other and trapped each other in the gravitational embrace, but they did not ever circularize. I don't have a version of this plot over here, but in fact, you might notice down here in the lower left, it turns out that if you're within 7 days of orbiting your M dwarf, you're going to be in a circular orbit. Always, 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 because the tides will force you into a circular orbit, just like you see in various other places in our solar system, like the moons of Jupiter, yanking on each other tidally. So there are no circular orbits beyond about 10 years. All right, I'm going to very quickly, because I don't want to use up too much time, talk about the K-dwarfs. And if you've been paying attention to the news as of late, you might have noticed in January there was a big splash from our group. And this is all about the K-dwarf work we've done. We started this later than we did the M-dwarf work. It's not as mature. We're doing all the similar kinds of things, looking for activity, looking for companions, and pushing towards planets actually orbiting the K-dwarfs. But one of the big results that came out last month, the big AAS meeting, was that we now have spectra of more than 2,000 K-dwarf stars, all within that 50 parsec horizon I mentioned before. We've now discovered that about 8% of them are either too young or too active to have any place habitable for a planet. So you can take that sort of roughly 10% off the table from activity or age alone. There just hasn't been time for any biological activity to happen because they're, a few million years old or a few tens of million years old. Or the other bit of work we're doing that was not caught in this particular press blurb was that about 20% of them have other stars near them. So roughly 30% of the K-dwarfs you can remove from the table and make your searches for planets that have life on them much more efficient because there's not going to be anybody home there. I like these two particular articles. There are a whole bunch of them. The one on the left, the folks who do these kind of things always want to pick the picture of a planet that looks really nice to live on. On the left, they did that. There's a little habitable world, it looks like. But I love the headline on the right, hundreds of nearby stars flagged as prime candidates for life. And then they show that picture of a planet. I don't think that one's going to be very habitable unless you want to live on some place that looks like Mars. So, some key results of the work that we've done over the years. We now have 55 papers in this astronomical journal series called the Solar Neighborhood that I believe John mentioned at the beginning. We've discovered, as I mentioned, 39 of those star systems within 10 parsecs. That's 14% of all the star systems known so close to the sun. And one little group of people did it. So don't ever let anybody tell you that a small group of people can't change knowledge, because I'm really proud of this. This is what I spent most of my career pushing on, and I think that we made a dent that mattered. We now know for the first time that 3 out of every 4 stars are little red dwarf stars. And in fact, if you add them up, in various ways. You can add up the mass of these things. They're very small, but there's so many of them that in fact, the M spectral type of star accounts for just over 50% of all the mass in stars. So there's more mass in M dwarfs than everybody else combined. You can also look at the real estate where you think there might be liquid water around each of these. That's very thin for any particular one star, but again, there's so many of them. If you integrate and add up all that real estate, there's more habitable real estate around M dwarfs than there is around any other kind of star. So these are great places to look. There may be some issues if you're orbiting a red dwarf. Maybe your atmosphere doesn't last on your planet, but that is TBD. We're not really there yet. We now know that M dwarfs have rotation periods we can measure and we can get their ages out of that. And we know that they have spot cycles like the sun. So that's going to affect you if you're an alien living on one of those planets. And we know that there are very few circular orbits, at least for stars, going around these if you're further away than about where Jupiter is. So a few AU from the sun in 10-year periods, you just don't have any circular orbits anymore. So that's going to wreck any planets that wanted to be inside. For the K dwarfs, we now know a lot of them are good for life. I didn't mention yet, but it turns out because they have longer lifetimes than the sun, they're probably among the best of all stars. Some people call these the Goldilocks stars because they last longer than the sun, but they don't have as many issues as the M dwarfs might have. And what I didn't get a chance to talk to you about tonight is that some of the work we're doing with Tim Johns at the telescope right now, he's hot on the trail of yet another hot Jupiter. These are the sort of big puffy planets that have migrated in close to their stars and orbit in the matter of days or weeks. And we can see those at that second telescope that we took over in 2017. And we're collecting the data on those, in fact, at this very moment, trying to get it to hone the data and get the orbits down. But if there's any one thing I want you to remember from this talk, it's that red dwarfs rule the galaxy. There's just no doubt of that. They rule it in numbers, they rule it in mass, they rule it in habitable real estate. So I'm hoping that this gave you a quick tour of a piece of the universe, right? We're all used to talking about the solar system that we live in, that has our four little terrestrial planets, a couple gas giants, and a couple ice giants. Now, hopefully, I've introduced you to the solar neighborhood where we have discovered a lot of these new nearby stars, almost all of them M dwarfs. But of course, that's just one small piece of a larger galaxy. That's the picture from down there in Chile. There are an awful lot of stars out there. I would argue that all the textbooks are wrong. And when you count up all the red dwarfs, the Milky Way itself is going to have 1 trillion stars. It's probably 2 to 10 times what most textbooks will tell you. And finally, of course, that's just one galaxy. We have all these other galaxies out there too. And so I think there are lots of cool places to look and lots of science to do. And I'm still going to come back to my big questions. What is the universe made out of? When it comes to stars, RECONS has the answer. We have now determined what that answer is. Check that one off. We are in the game finding the planets, and everybody in the world is rushing towards trying to find the life on the planets. I'm hoping to hang around long enough so that we detect life on another planet. I don't know. It's technologically very difficult to do, but hopefully we're getting closer and closer every day. But one thing I will tell you, don't forget your map of the solar neighborhood, and you definitely can't do it alone. There's no way I could have gotten any of this stuff together for this talk or presented any results I could that I did show you tonight without a lot of really smart young people working hard to try to pull this all together. So we live in a big universe, and it's nice to have company while we're exploring it. I'll leave it at that for the main part of the talk, and then we can get to the bonus round.
Um, Questions from our live audience?
So I can hear something happening. It's very hard to understand exactly what words are being said.
I'm just asking the audience if they have any questions, and we have a hand up.
I can hear you. Yes, I can hear you now.
Okay. Hold on. Before you're done, I was hoping you'd tell us a little bit about your Astronomy on Tap program.
Oh, Yeah, so we're one of many cities now in the world doing astronomy on tap. And what we do is once a month, we go to typically a microbrewery type place. And in the microbrewery, we give a talk and people drink and maybe have pizza or French fries or whatever they want to get that are there. And we just cycle through all kinds of crazy topics. We've had the dark collision with an asteroid. We've had crazy worlds out there. Um, we've had life in the universe, of course. We've had the Big Bang and what happened at the beginning of the universe. We've had how do you measure distances to galaxies, all kinds of stuff. It's once a month here in Atlanta, and a lot of cities have them. I don't know if Newark has one or not.
It may work. Good. Hold on, here's another question. Uh, you measured the percentage of M dwarfs and K dwarfs inside 10 parsec radius, and are you extrapolating that to the whole galaxy and whole universe? That 75% of the stars are M dwarf.
Yeah, so I heard most of the question, I think. I believe the question is about how does the 10 parsec sample compare to the rest of the galaxy and the universe? Um, so our assumption here, we're being Copernican, we're not the center of everything and we're not special. So we assume, and with this larger sample going out to 25 parsecs and then 50 parsecs, we can actually start to pull the numbers together. And we're going to see if the numbers we have from 10 parsecs are consistent. We can certainly do that all the way out to 25 parsecs now because we've got the mega sample of the 3,000 M dwarfs and all the other types of stars that are in there. Yeah. So, I mean, they're going to be the rare cases where you're near an O star or a B star and life will be different there. Or if you're in a globular cluster, for example, where the stars are much more tightly packed, those are different environments. But we think that the disk of the galaxy, at least, and other galaxies is probably going to be pretty similar to what we have here. Did that answer your question?
Hold on. No. We could be inside of some kind of like Central Park in Manhattan, or galaxy itself is about 20,000 light years, and then if you measure like 20 uh, light years of radius, then it's really, really small sample. So we could be inside of like New York City, and then you measured maybe
Yeah.
like Park Avenue. So we cannot know that, and we
Okay.
cannot
So
even.
here's what I can tell you for sure. These two larger samples that we have, right? So the 50 parsec sample is now 125 times the volume. So it's a much larger region than the 10 parsec sample. And we can map the K dwarfs out through there. And we can look at equal volume shells as we move out. And we know that the sample is within a few percent exactly the same size. So we know at least out through that much of this spiral arm, things look exactly the same. And other than those couple strange cases I mentioned, we don't have any evidence that things would be very different anywhere else. Now, as you leave the plane of the galaxy, the numbers drop off, and you don't have any massive stars because they've all either blown up in supernovae or they've converted to white dwarfs. The only ones that are left above the galaxy are the K and the M dwarfs because the G's and the A's and the F's and the O's and the B's have already done their thing before they can actually get what we call disk heating and perturbed until they're further above the disk. So within the disk, I think we're good to go. As you go about above the disk, I'm even happier because then all you have left are M dwarfs, K dwarfs, white dwarfs, neutron stars, and black holes.
Are there any other questions? Any
We've got a
questions
couple
from?
questions.
Yes.
Yep, I think you're muted.
Somebody needs to unmute themselves. Cliff, did you ask them to mute yourself again? Who are the questions?
Oh, okay. I have a question about the K dwarfs. I
Yep.
gathered from what you said that if you were on a planet orbiting a K dwarf in the habitable zone, you would be much less likely to lose your atmosphere than you would if you were in orbiting an M class dwarf.
That's the current thought. And the reason is that in order to orbit the M dwarf in a place where water would be liquid, if you demand water, that's another if, but if you demand water, you're so close to the M dwarf that the activity in the ultraviolet and X-rays will strip off the atmosphere in a short period of time. I always like to say, however, because I'm a defender of the M dwarfs, however, the Earth is now on its fourth atmosphere. So it doesn't mean that when the M star is young and stripping away the atmosphere, that you can't create another atmosphere later. So I don't really think that's a ender for the M dwarfs. It's just that the K dwarfs people are more comfortable with, although now it's starting to become known that they have UV fluxes that tend to be high for longer periods of time than stars like the G stars or maybe the M dwarfs. So everything's got a catch to it. But again, because the numbers are huge, if you have a trillion options in the galaxy, I think it's going to work out some places.
The other question I have is that if you compare our solar system with all of the other uh, planetary systems around other stars that have been reported, it's looking like the solar system is pretty peculiar. Do
Well,
you think is that a likely to turn out to be the case, or is there some selection going on where we're
there,
not really seeing the outer planets?
got it. We're not seeing the outer planets yet. Um, we have this really long-term 30-year program. Virtually no one else in the world has this kind of stuff. And that particular program is not super sensitive to planets. We would have seen a Jupiter going on Proxima Centauri. We know it's not there from our data. And sort of the nearest 10 red dwarfs that we're following, we can eliminate Jupiters. Turns out, unfortunately for us, no one knew this when we started the project, that small stars don't make big planets very often. It happens, but not very often. But anything beyond about 5 AU where Jupiter is, it's really sketchy because you need 10 or 20 or 30 years of data to really nail it down. And nobody's got it because the average funding cycle for a grant is 3 years. And I've been fortunate and I run marathons for fun, so I just don't give up on things. And I keep going back and keep going back and keep getting funded. And so we can keep doing this work. But most people aren't that fortunate. And so, yeah, it's a huge bias right now. But I will also guarantee you, I just saw this a few days ago. They've now found a system that has a rocky planet, two gas giants, and then a rocky planet outside of it. And that's the first time we've seen that.
Right.
So if you can make up a solar system, I will bet you $100 it's there. Who wants to have a little bit of fun in the bonus round?
Yes, please.
Let's do it. Okay. We like talking about stars, right? Proxima Centauri is the nearest star. If nothing else, we astronomers get to supply people with ideas, and those people sometimes include authors. One of my favorite hobbies is to read science fiction books. And so I'm just going to give you a few science fiction books here. Proxima by Stephen Baxter it's a great book. And in the case of Proxima, we send people there, they land on it, they find that there's life on one of the planets there, and they run into all kinds of certain issues with those life forms that happen. I think these are the ones that are triaxial all the time, and it's an interesting read. We now know that Proxima has at least two planets, and others have been reported. So it could be, maybe, that some of this science fiction will turn out to be true. Another one of my favorite book series are the Roche Worlds by Robert Forward. This is around Barnard star, the second nearest star to the sun. And this is a good place to go because historically, Peter Van de Kamp thought there were two gas giants going around it. We now know that's not the case, but we now think there are at least four planets going around Barnard's star, and they're all small and rocky planets. In this particular book series, Roche World, you go to, they're using real technology that could happen. Robert Forward was a physicist and he wrote books that actually make sense. And so here's a little mock-up of the proper motion of Barnard's star. You might have heard of this star because it is the fastest moving star in the sky at 10 arc seconds per year. That makes some sense because it's the second nearest star to the sun, nearest star system. Alpha Centauri with Proxima, of course, has 3 stars. But in his worlds, one of those worlds that's found is called Roche World because it's got 2 lobes to it, and they're so close together that they touch when they get close enough together, and water flows from one to the other, and there are life forms on there that live in the oceans. It's a very cool book. So that's nearby star number 2. Then, of course, there's nearby star number 3, Wolf 359. I don't know if anybody in the room is a Star Trek fan or online, but of course, this is the Great Battle of the Borg, where I guess the Federation loses 39 out of 40 ships, and a lot of it is because Jean-Luc Picard was taken over by the Borg, and as Locutus, he gave them information and led to a wipeout of Starfleet at Wolf 359. I have actually asked students on qualifying exams in the past, if a Borg cube passed in front of Wolf 359, could we measure the transit? And the answer is, it's right on the hairy edge of technology right now. So if they're there, we're almost able to detect them. 0 planets on Wolf 359 so far. Then there's this book, series of books also by Robert Forward. This is Dragon's Egg and Starquake. And this is really cool because this is a nearby star, but temporarily. It turns out there is a neutron star that passes past the Kuiper Belt, between the Kuiper Belt and the Oort cloud out there. And we send a ship out there and we meet some of my favorite aliens of all time called the Chila. The Chila are about the size of a sesame seed, and they live on the surface of the neutron star, and their lives go 1,000,000 times faster than ours because they're on a completely different environment. And this is a scene where there's a war between the Chila on the surface. These tiny little guys, of course, are dealing with immense gravity and fast evolution. And during the time in which the Earth spaceship is orbiting Dragon's Egg, the neutron star, the Chila are primitive and they go whipping by us in technology in a matter of a month because they live so much faster. Fantastic book. But I was really setting all this up because of these 2 stars. Tau Ceti is the 10th nearest star system to us, and 40 Eridani is the number 49th. Can anybody guess why I'm bringing up these 2 stars?
One of them is Vulcan, right?
Vulcan.
One of them is Vulcan.
Area A does have Vulcan, but there's a new, fresh reason. Tau Ceti now has 4 planets. 40 Eri has 0. It's in a triple system, and the white dwarf and the red dwarf next to it are close enough that maybe it disrupted any planets that were being found or could have formed. So this is why it's important to know your nearby stars. But you might have heard of this book called Hail Mary. And there is a movie coming out on March 20th, and it involves both of these stars, Tau Ceti, 40 Eridani, and the sun. And it is a fantastically good book. All of these books have either got, so I've read hundreds and hundreds of science fiction books at this point, and I grade them all. This one got an A+. All of these books I'm giving you either got A or A+. I would recommend you to see or to read any of them. And I cannot wait for this movie because all the trailers I've seen and all the stuff I've read about it looks like they did a good job. And it has all kinds of twists and turns that are really fun. So I am recommending to you, even before I've seen it, go see Hail Mary. Better yet, read the book.